So I'm going to talk about one-to-many UCT transports, which, as you can imagine, has a lot in common with my next talk after Morad's, which is UCG. And clearly, to me at least, this topic stands on its own because we really, really want one-to-many UCT transports. I'll start by stating the problem in so many slides. First, you all know this. When OpenMPI starts, it chooses a component, and then the component, when it wants to call something like MPI Bcast, it will pass control to the chosen collective component. The chosen component can either A, do point-to-point using some of the point-to-point components we all know and love. B, it can call some external library. Spoiler, this will happen later in the talk. And if push comes to shove, fail and fall back to another module, which would be probably unfortunate. This is an excerpt from basic broadcast. This is just one piece in a really long code that basically says, send to all my children, right? You can see this loop on the outside, and in the inside, you can see the I send. And presumably, this is the most basic implementation of Bcast you can imagine. To add insult to injury, I'm pretty sure it's a flat one without like levels, but I wouldn't, don't take my word for it. You can easily look it up in call-based Bcast in OpenMPI. This is what we want to avoid. So a very small introduction to why UCG is there in the first place is we observed that while today, unless you have a specialized collective library that is focused on that, what OpenMPI would do in a lot of cases is do this three send, assuming you do have three children. Whereas, oops, this is jumping, sorry. Whereas if you had the collective library, OpenMPI could just call Bcast and you can do, UCG does, these three sends inside the OpenUCX. I'm not going to go into UCG and how it's positioned, but I will say this. You can imagine that if these three sends are identical, there's probably a lot you can do to optimize them. It's not going to be 3 times the cost of a single send. And this is what we started the project with, by project I mean UCG. And on a more general note, you really want to batch identical sends and receives. So I know people say premature optimization, but I actually think too many abstraction layers are the root of all evil because they happen to make a living out of premature optimization. So yeah, you can imagine. And also, to be more specific, this is an out of context chart I stole from XKCD. It actually tells you we spend a lot of time choosing what we want to do instead of actually doing it. So this applies to sends, obviously, because like I'm kind of exaggerating here, right? But still, I think the cost of making a decision like do we send it as a short or a B copy or a Z copy is something we may not be able to avoid, but we can definitely do it once for a multiple number of sends, which is what consolidation of batched so-called sends and receives is all about. Right, so this is also something everybody here knows, but I feel it's a useful slide to demonstrate my PowerPoint construction skills. Anatomy of a collective operation. So obviously you have hierarchies and we can't ignore that. So this flat tree that I mentioned earlier will probably not fly in any production environment. So to illustrate the levels, we have the core. If you happen to use hyperthreading, God be with you, CPU socket and host are probably other levels useful to have. And finally, network, illustrated here as just one level if you have this humble 10-node cluster. But clearly, if you have more, there are more levels here, and that's a lot of fun. So finally, after 3 slides, the problem statement. Problem statement is reducing the latency of a single level of one-to-many communication. Clearly, constructing the levels is also very important, but this is out of the scope of this talk. I will only focus on You have one sender, you have n receivers, and what's the best way to get data from the sender to the receiver? So some factors that go into should probably be taken into account. Probably no library in the world will take everything into account because that's a lot of man hours, but it's good to put it on the table just in case. On data pattern, broadcast versus scatter. So I got a question practicing the slide saying, okay, scatter doesn't look like what you want to do because clearly everybody wants different information. However, if you're doing a scatter of 8 bytes and you have 4 destinations, you're probably better off sending this redundant information compared to the alternative, which is to allocate 8 bytes for every destination and send 4 messages. So I argue that scatter in some cases is very useful when combined with one-to-many communication, even though that's not 100% the pattern. Data size, clearly in UCX, there's what we call short B copy, Z copy, but clearly any like different sizes of data probably need different mechanisms to handle them. That's easy. We know the same for point-to-point. Process affinity probably makes a lot of sense. Actually, this is probably very much off topic, but just to give an example, I actually found that in some cases there's an architecture or software flaw, and KNAM actually does worse on core-to-core adjacent core copies than on CPU to CPU copies, which makes absolutely no sense. So on some specific occasions, like all the stars are aligned and copying to a different CPU is faster than copying to an adjacent core. I still don't know what the reason is. We're investigating this, but this is just to say process affinity matters. Memory hierarchy also matters. Typical process imbalance very much matters. Okay, so we actually...
Alex, is this with KNAM you observed it?
Yes, KNAM, 8 megabytes. If anybody has seen this already, please let me know. KNAM, for some reason, on 8 bytes, he has this horrendous drop in performance, and CPU to CPU is 2 times faster than core-to-core adjacent. Happens only on x86, not on ARM. Funny stuff, I know. If you have an idea, please reach out to me. I'm very curious. We're debugging this.
Maybe
anyway.
HW log mapping of the system is busted or something. So you think it is just in core, but it's not.
So
well, we did bind it to core.
So I think that for 8 megabytes, you're going out of cache. So, and the memory copy in the kernel is doing ref move SB, which is less efficient in this case.
So that's what I thought, but it doesn't. It stops happening at 16 and 32 megabytes and so on. So there's a sweet spot where everything goes wrong. And then beyond that point, everything is okay. Sorry, I don't have a lot of information on this. I just got this mail from China today, and I didn't have time to address it. But you should know that like weird stuff sometimes happen with, and clearly this process location is very important for latency. Probably protect. Yes.
The question: how much you really have to pay attention to KNAM since it's like not really maintained.
Yes, I know. I told them that, but like. Yeah, for various reasons, I do need to reply to their email with something decent. So I can't really dismiss them, even though I think it's not a cost-effective endeavor. Yeah, but that's right. Okay, so going back to this, process imbalance matters more than we think. We actually have quite a few methods that actually, it's a bit of a pickle because OSU and its family is very much used to benchmark these kinds of communication. However, OSU happens to be perfectly balanced, right? No compute at all, and everybody's trying to do this at the same time. So this is very not what happens in real applications. where processes approach you over time. So behavior on memory and contention on locks is very different between balanced and imbalanced processes. That's also very relevant here. Other non-MPI considerations, data availability. So bcopy is a good example because it gives you a way to address gradually arriving data. So this is one thing we probably would like to see in one-to-many communication in some cases, again. And last but not least, this is something that's kind of advanced. I even included it in other slides, like future ideas, but what do you do with the buffer afterwards actually makes a lot of difference. I think I mentioned it as a comment to a discussion we had with Yossi the other day about like what kind of hints. So if you know what you're going to do with the buffer afterwards, specifically if you know it's going to be like a read only or a write only buffer, then maybe you want to do this one-to-many communication in a different way. Another problem, which is probably very has a lot in common with this one, but the solution is somewhat different, is many-to-one. Clearly, I'm going to spend most of the time talking about the broadcast and the one-to-many. I am going to say, clearly, we implemented the other way around for reductions, and this is also something very interesting to us, but as I said, has a lot in common. I think this lecture covers both of them pretty well. Can we even consider zero copy? So yes, we can. Usually, this is exactly one of these cases where I say, okay, if somebody wants to broadcast data and every child promises he will not modify it, we can presumably just map our memory to the memory of our children and then tell them, okay, look, here's the data as long as you promise not to spoil it. So this is also something I think we should consider, even though MPI will not give us a good opportunity to use this one yet. Maybe in the future, who knows, hints and stuff. So initial thoughts. First, it looks like, both based on intuition and based on empirical results, for small groups like 2 or 3 ranks, you're probably better off using P2P. First, you have P2P anyway, so you might as well use it, the overhead. Like you already have this facility lying around, and like the additional overhead of the code of like arranging the synchronization between the processes, probably not worth it. So that's first. Next, you probably want to reuse some of the mechanisms and API you already have for P2P. With API, I do mean UCT API, and by mechanisms, I actually mean code. So as little changes to UCT as possible would be preferred. Obviously, no changes is a bit hard. Morad will talk a bit about this later. Not just for send receive, other mechanisms are also probably very useful. We probably want to reuse our cache and buffer pools and all the mechanisms we already employ for point-to-point, for one-to-many as well. The tricky part is actually not how to place the data, it's how to synchronize the number of ranks. This is an opinion, not a fact, but it seems like, especially with something like broadcast, it's pretty straightforward. You take the data the user told you to, maybe 8 bytes, or most of the tests focus on small messages, and you place it within some buffer everybody can see. So the challenge is not that. The challenge is, how do you know this buffer can be later reused? This requires every process to tell you, yes, I got the data, you can now reuse the buffer. So that's the synchronization. Clearly, same problem with reduce, but this is on the, you can say it's more visible on the critical path because you need to make sure everybody sent you the data before you can actually use the result. So we can choose to put this burden, and I'm going to mention this later in the slides, either on the root or on the children or leaves, whatever terminology you prefer. So next, I'm going to talk about collective operations on shared memory, and then we're going to switch over, and Murad's going to talk about his work for network multicast. So we have shared memory today. Otherwise, I wouldn't have a lot to talk about. Shared memory component in OpenMPI exists, and we have various closed source collective libraries that do shared memory. What's missing is first, we really want to combine shared memory with something else, which we feel that the levels of abstraction with the current solutions don't provide. For example, what if we want to use the same buffer, the same area of memory, both for shared memory and for RDMA? So clearly we need to register the memory, but let's assume that's taken care of. The same buffer, the same region of memory has to belong both to the shared memory transport and to the network transport. This is not trivial in a lot of the solutions we see today, because these are kind of disjoint modules, components, whatever you call them, and they have pretty rigid APIs. Next, does one size fit all? By that, I'm saying, okay, if you have an 8-byte send, or if you have an 8-byte reduction, do you always use the same method to achieve this? So I say that has a lot to do with the transport, and you need to have some intimate knowledge with the hardware you have to find the best solution. And also, I'm kind of pointing at this, kind of trying to bring home the concept of abstraction is the root of all evil. So how do you know if you can or cannot use atomics? For example, specifically atomic add. Maybe sometimes you can, maybe sometimes you can't. Clearly, this is not just a shared memory question. That's also a network question on the network transport. And clearly, you want to avoid memory copies like the pandemic, which is now very popular. And last but not least, all these factors I mentioned, you need to take them into account. Either you make some clever decisions in the beginning and then apply them to every new shared memory collective call, or you do something in runtime, presumably not too complicated, which will make a dynamic decision based on something that maybe changes. So I don't have a definitive answer of what's right. I have an answer of what we did, and I'm going to talk about this next. So first, a very small and short introduction for how we do point-to-point today. So typically, though UCX is one-sided, we typically have both sides at every given moment because the child sends to the parent and the children send to the parent and the parent sends to the children, or root and lifts, whatever. So we would have two FIFOs, one for sending and one for receiving from that same host, even though they're not coupled together like a QP or something. And we have this UCT FIFO element, which contains active message ID, length, buffers, buffer itself, and flags. And you have a head and tail like producer consumer, that's fine. So on the left, you see an illustration. You have three. If you have 3 arrows, that means you have 6 of these FIFO elements, FIFO objects, and that's how you do. So what we added are 2 additional FIFOs. They are both placed on the root for fan in and fan out. That means if you want to send to somebody and he is the root, you send to his FIFO. And if you want to receive something from the root, you poll his FIFO for anything incoming. Clearly, you don't want to have a lot of people broadcasting, because that means you would have to poll on everybody's broadcast queue. Fortunately, in MPI, we have a lot of tree-like topologies where you would typically receive broadcasts from only one root or one parent. Almost across throughout the run. Clearly, if you have lots of communicators, that's a corner case we can handle at some point. But in general, we will have a very similar structure to what we have with point-to-point in shared memory. And we actually didn't change a lot of code. Maybe, if memory serves me right, maybe 3 or 4 source files that actually inherit from shared memory point-to-point and extend this flag pending, which, as you can imagine, is how we synchronize how many senders have already sent to us, or how many receivers have already received from us. And if as soon as pending reaches the number of processes in the group, we can call it a day. Speaking of this, okay, 20 minutes, fine. Right, so we have 4 modes of operation. By have, I mean I kind of coded them, but if you're asking me about performance and have I tested and compared them, that's somewhere in my to-do list. I promise I'll get to that at some point, but for now, here are the 2 main ones, and you can imagine there's going to be a comparison down the road in just 2 slides. Batch mode, this is the illustration. If we have this process 0 and processes 1, 2, 3 sending to him, and they send data 111, 222, and 323 correspondingly. In the batch mode, you have this one region of memory. Supposedly, the distance between brackets is at least a cache size, so they don't step on each other's cache line. So when somebody is ready, he just writes to his cell and increments the pending. And when pending reaches 3, we know that all the buffers are ready for the root to read them. Note that, yes, this is many to one, although the talk is about one to many. It's because it was hard for me to turn these illustrations around, but trust me, the other way works very similarly. So in centralized mode, we have we clear the last bit of each cell. We actually clear the byte and not the bit because it's easier to work with. So at any given point where the buffer is full, the sender would mark his last byte as 1. And then what happens is you remove the dependence or the contention on this pending variable, which originally had all these requests. I remind you from my previous talk that we have up to 64 cores per CPU. So 64 guys at the same time incrementing pending is no good. And if you're looking at the host level, that's 4 CPUs. That's a lot of processes. So centralized is what we use for reductions, and the batch is more about more for the one-to-manys, the broadcasts, where the processes are not as balanced, so the contention on the pending doesn't bother us that much. But clearly, we can use either for both cases, and we can compare results, and it would be very interesting, maybe even a paper. These are the ones that are more generalized, and you can see in the illustration, I changed the arrows directly between P1 and P0 to some kind of repository. It should have been a pipe, but it looks like this. Sorry about that. So these are the main modes. We have 2 other modes we wanted to play with, and these are the locked and the atomic. Those are specific for reduction. The locked one is you have a lock. This is actually the original reason why I added into UCS spin lock the support for multi-process flag. And basically what it does is it acquires the lock, it reduces the data, and then it releases the lock for the next guy. It increments pending because it's easy in the code flow. We already check it, whatever. The atomic mode is actually interesting because both in shared memory and in RDMA, we have this mode where we can, for some operations, for integers of certain sizes, we can actually do the reduction in one atomic operation without disturbing the lock or polling or waiting or whatever. So it would be interesting to see how atomics compare. I should say, probably if we run OSU, they will not fare as well with compared to the others. I assume that if we actually use on real applications where there is real load imbalance and the contention is not that great, this might do better. But we're a success-oriented company, so we start with what works well for benchmarks, and we really want to research this at some point. Right, so some comparison just to, I'm not sure this is the main takeaway, but I do want to show this to kind of illustrate we have a lot of considerations at every given point. So In the first two modes, the burden is on the receiver because both in batched and in centralized, somebody has to poll for the messages and see if it arrived. Whereas in locked and atomic, burden is on the sender. The receiver kind of has this one flag saying if it's complete or not. Mutual exclusion, we use different mechanisms. In the first one, the pending is treated as atomic. So either we lock to it to get it, or we do atomics to increment it. Centralized has no mutual exclusion whatsoever because everybody marks their last byte, but it has other costs for polling. In the worst case, if you have 64 processes sending to you in centralized mode, you actually need to go over 64 cache lines to see that they are all indeed marked as done, instead of just going through this one pending. Locked and atomics have their own clearly locking mechanisms. And the last column is what I think is most interesting, mainly because I kind of presumed what the answer would be, but I have yet to compare the last two with the first two. I know for a fact that the low PPN is a bit better with batched, and high PPN is a bit better with centralized, but that has to also do with the way I think it also has to do with the way we implemented them. Long story. I assume that for large sizes, for reduction, we might prefer lock, not because I imagine 64 processes locking for the same region of memory. I really think this locked thing should be also cascaded and have multiple levels, but probably you don't want to waste the space of the buffer if it's a large buffer multiple times, like we do with batched and centralized. And atomic clearly works for specific operations that atomic supports and for imbalance where the contention is not great. Changes, we did quite a few of them. How am I on time? Well, UCS. So UCS has the multi-process lock. UCT has most of the logic, new transports, new endpoint and interface named the sysv or POSIX or whatever is there for underscore Bcast and underscore incast for a broadcast and reduction. UCP, almost no changes, just added a couple more lanes to accommodate Bcast and incast selection. And UCG obviously needs to be made aware of this and actually use these new transports. Last slide, I promise. Lots of numbers. I don't expect people to actually go over them, but this session is recorded, so if you really want to, you can. There are three kinds of results here. It's a packed slide, I know. First is x86 versus ARM. ARM actually performs really nicely on the same 8 bytes. Here you have the broadcast and reduce. I chose very unorthodox numbers, 3, 10, and 18 as PPN. The reason is because the Xeon had 18 cores, Xeon 18 cores, and this particular model, and 10 is kind of in the middle. Clearly, one more thing, if you ask for a power of 2, the code opts recursive doubling, and I didn't want it to do that, so this was a quick fix. So this is why the strange numbers, but the bottom line is broadcast and reduce on ARM do quite nicely. The second part is point-to-point versus one-to-many. This is actually like the one to beat. Point-to-point is the way we did things so far, unless you had the specialized library doing something else. So one-to-many transports on Bcast, you can see on the left, and on Allreduce on the right. So Allreduce includes Bcast and reduce and then Bcast. So you can see that for small messages, difference is not great. We even see some decrease. Actually, yeah. And for large numbers, clearly it's better to use a multi-level approach, right? So this is something that we will probably not do. This goes up to 80 ppn, but at this point, I figured it doesn't make sense to go a full 128, which is what I have in the lab, not the 256 variant, which is very rare and expensive. But we have nice results for the middle section, which is probably the radix we want to use with some anomalies here. This is last. This is actually, yes.
What is point to point? What does it mean? Is it like tuned?
It means I use the UCT point to point shared memory transports. So I did a loop doing send over sysv. Yeah, that's the one.
Josh, it's UCT point to point operations.
Okay.
Yeah, UCT. That's the one.
So you're saying that you implement a broadcast with UCT point, right?
So the column that says point to point is if you have a ppn equals 5, that's 4 UCT send commands, and the column marked as SM is this new transport I added to UCT, which basically places the data and everybody copies from the same place.
Gotcha.
So on the left is Bcast, on the right is Allreduce. At the bottom, it's actually the same comparison, just with increasing message sizes. I have to admit that I didn't invest a lot of effort into the large messages, even though it is important, and I expect we might be able to improve it in the future. But if you're curious, it does basically the same as point to point. It just uses the big mapped buffer instead of putting stuff in line inside the FIFO element. Both for P2P and for shared memory, it does roughly the same. And if the buffer is really large, it actually maps the user buffer and the same as point to point, just with this modification that the FIFO element is available to many nodes at the same time. Questions about this before I move on to Morad's talk. Go ahead.
Last slide. Can you go back to the last slide, please?
Sure. Yeah, I'm here.
In this measurements, what's the deviation that you see? The reason I ask is on your 8-byte broadcast, you see, there is a performance improvement is not, say, linear, right, or constant.
Yes. Yes, I have to admit these results were obtained this week. I'm a bit embarrassed by it, but that's the honest to God truth. So I don't have a full explanation. I do have some explanation. For example, if you look at the very strange gap between 63 and 64, this is, as I explained, it switches to recursive doubling, and I didn't have a good way to control this. This is just the way it came out, so I had to write it down.
Okay. And also, it's very tricky in a shared memory transport to have very less variance. You have to be really, really careful and methodical how to make sure that you quantify the variance. So it's not.
Yes.
And when you have at 80 cores, I can totally imagine that. Yeah. Yeah. Thanks.
Yeah, so this is why I put disclaimers everywhere. It's very preliminary, and I promise we can probably do better, but I didn't have time to by today.
And Alex, so it's like semantically inside in the transport, is it doing like load store types of semantics, or like one-sided semantics, or doing two-sided?
So it does two-sided, and so yes, the two-sided semantics is the one being used. We don't have I'm not sure. I'm pretty sure one-sided will not work if you test it right now. But if you want more details, the code is available online, like everything. I have in the other talk about UCG, I have links to specific places in the code, so everybody can feel free to take a look.